Action.
We're good.
Yeah, the function. Oh my God. Okay. Actually, I'm going to put off magnetic phenomenology until the end, so that if I run out of time, it's actually not so important to this course as being able to deal with boundary conditions and deciding how you're going to find out what the magnetic field in a specific problem is. All right. So I have actually defined a few things over here that I defined the H field for you and the magnetization, and we've been talking about magnetization. So I don't have to take any time, I think, to define that relationship. But what I should end up with here are a couple of rules with respect to the boundary conditions. So we ended up with rules for the electric field over there, which were that the electric field parallel to a surface is continuous across the surface, right? So I think we wrote E1 parallel minus E2 parallel, where I have a surface and I've got medium 1 and medium 2, or yeah, medium 1 and medium 2 is equal to 0. And we had that D1 perp minus D2 perp is equal to 4 pi sigma free. So if I just have a dielectric, then I won't have any free charge on it. And I could have a polarized dielectric, and the D field is continuous across the interface, right? I'm going to I'm going to state some rules for the H field and the B field in a couple of minutes. But before I even do that, I'm going to solve a couple of magnetization problems. Have we confirmed this? This one?
Yeah.
Okay. And have we confirmed this?
Yeah, you need the 1 over C.
Someone came up and fixed it.
I did.
You did? So it's confirmed?
Well, the book never does it, but
Oh.
I subbed in the equations the book had.
I'll check on that.
You missed this.
Let you know.
Why is that in?
But
Is
only
that
if I
an
remember.
is that an L?
Is that on?
Yes.
I did not do it.
Give you a hint, you gotta call
We're not talking about that on camera.
Yeah, I know. I said I'll tell him later.
Okay, good. All right. So, what about the so then what about the B field? Due to an infinitely long, I'm going to do the easy one and then give you homework for the hard ones.
Har har har.
Due to an infinitely long rod of magnetized material. All right, goes on and on, my friends. So the magnetization in that material, I'm just going to write is Z. And we want to know what the B field is in various regions as well, right? The bulk current, magnetization current, is the curl of the magnetization. Magnetization is a constant, so that means that the bulk current is 0. Right? The surface current, wait, we do have a surface current, right? The surface current is the magnetization crossed into the normal to this surface. This looks cylindrical to me, So I'll take that to be R, right? And so it's M cross R hat, where M is that, so it's M Z hat cross R hat, which is going to give me, say what?
Phi hat.
Yes, but I would just, is it positive phi hat? E cross R gives, yeah, positive phi hat. All right? So the surface current goes around and around. But it's even better than a solenoid because there's no net current traveling that way. All right? There's just current going around and around. There must be a song. All right. Now that I know what the current is, I know this is a current density, right? I can just use Ampere's law to solve this problem. And it's even easier than for the solenoid because it's just a surface current density. So I draw a little surface like that. I write down, making sure I've got my units right. B dot dl is equal to some of you know that I'm like simultaneously teaching Physics 2 in MKS units, and that's my big problem right now. Those of you who are TAing in Physics 2 are having the same problem, I think. You're just staring at it, trying to remember, is there a 4 pi c here, or is it mu 0 and epsilon
Well,
naught?
mu naught is just 4 pi over c in to
Stop confusing
translate.
him.
Okay, don't confuse me. 4 pi over c. Okay, that's the net flux, all right? So that's actually 4 pi over c k times L. K is the magnetization current that I derived over there, times the length of this region that I'm going to take here, L. All right? And this side here, I'm actually only going to have magnetic field on the inside, right? And I can prove that by drawing two Amperian loops here. One that encloses the whole thing so that I have no net current, and I know that the magnetic field has got to be 0. And so this ends up being 2BL. L goes out, and I end up with magnetic field is equal to 4 pi over C K M. Yes?
Yeah, minus you dropped in c when defining km.
Oh, I dropped a 2. And I dropped a C here. Was this
Yes, as you got there.
C? C?
Well, then you
No. Made that substitution.
it's just in your definition of km.
Yeah, okay. That makes a difference here. All right. Because I'm just about to rewrite this as 2 pi C goes out M. All right? So the magnetic field in the material is just related to the magnetization. Did I lose something here? Oh, what? Oh. And I think I screwed up. Actually, the magnetic field on the outside is 0. So there's just a 1 here. And then there's no 2 here. And that makes that 4 pi out. And that's what I want. Magnetic field is 4 pi out. And if the H field, coming back over here, is just due to the free currents, we had no free currents in the problem, so we had to have V is equal to 4 pi m. Okay, so it works.
Everybody happy.
So that's the easy one. I think I'm gonna this time around I'm gonna talk about how you might do it, but I'm not gonna do the arithmetic in front of you. And I might assign the arithmetic as an exercise to the student. Have I assigned the upcoming homework yet?
Nope. Should we be scared of that smile?
Yes. But, and no, you see, you should really only be scared, I think, if you're a diligent student who does all your homework before Wednesday. Because by Wednesday, I will have figured out the easy way to do it. Or I will have said, whoa, that's hard, and send you an email that says, don't do the whole thing, just do it with MATLAB. Sorry, but that's true. All right. I wanted to choose one that was sort of an analogy to what we did with polarization. And so I'm going to take a uniformly magnetized sphere. Right? So I'm going to put on the inside, I've got a magnetization to this material. And then the question is, what's the magnetic field everywhere in the problem? The answer is, it's a dipole. Right.
Wait, where are the top and the bottom?
What?
It's a dipole, where was the top and the bottom? And the sphere.
Outside the sphere, it's a dipole.
Oh, okay.
Okay. Inside, the magnetization is constant. So B is equal to 4 pi m. Outside, it's a dipole.
Okay.
All right. We'll choose the z-axis to be along that direction. So, well, I mean, we're really going to work in theta and phi, but I want to define where I'm measuring theta and phi from, where I'm measuring theta from. And so in the material, the bound current that could give rise to the bound current that could, the magnetization that could give rise to a bound current, which we could calculate the magnetic field from, is 0, because inside the magnetization is constant, so 0. I won't give you this problem for homework. I'll give you one where the magnetization depends upon position. Yes.
It's still a dipole.
How about, I will give you a finite cylinder
Oh.
where the magnetization depends upon position.
Make it have an octopole
That's still
moment
a
just
dipole.
for kicks.
That one's good. I like that one. All right. Because, by the way, no. I could just give you a finite, okay, never mind. Sometime later today, you will find a gift in your mailbox.
We'll keep on.
Yeah.
I can hear Brian whimpering all the way from here.
All right. The surface current, the equivalent surface current here is m cross n. The normal is r, just pointing out in that direction. And so we end up with m sine theta phi hat. It's basically current, an effective surface current that grows as a function of distance from the ends to the center and then shrinks back down again. Right? So sort of the way that I drew it is probably not all that far off from what the surface currents would look like. Right? It turns out that this problem is already solved in Griffiths. Because what this actually is if I put a constant current density on the surface, a constant charge density on the surface of this sphere, and then just spun it, I would get, I would be able to solve for the magnetic field. And Griffiths did this. So I copied his solution. I have more steps here, but I'm going to skip them. Right? And the answer is, aside from factors of c and 4 pi, and maybe 3, that the magnetic potential inside looks like 4 pi m r over 3 sine theta phi hat, something like that. And when you take the appropriate derivatives of the curl of that in order to find the magnetic field, right, you should, if we did that right, find out that the magnetic field is equal to 4 pi m. So let's assume that that's the case.
With some C rather than
And I probably dropped a factor of C. So we'll pretend that we are particle physicists, where C is 1. And outside, it's 4 pi r cubed, the volume of the whole thing times the magnetization per unit volume, sine theta over 3 r squared by outside, right? Which is a dipole with dipole moment, little m would be the dipole moment of the whole thing, 4 pi r cubed m. Take the magnetization per unit volume, multiply by the volume, gives you an effective dipole moment, right? So again, actually, being able to use these bulk and surface currents, and then once I've got bulk and surface currents, to use Ampere's law or Biot-Savart to actually solve it, right? Turns out to be an easy approach to dealing with magnetized materials. Okay. I will put up more steps as far as that solution is concerned, because there are a few steps between here and there. It's about page. I'll put up those steps, but that's the idea. You deduce the surface currents, then from the surface currents you find the magnetic field. Okay? Yeah. All right. Let me talk a little bit about boundary conditions that we can use. Here's something we know for sure. Well, we don't know that for sure. But as long as we don't find any monopoles, that's good. Yeah, right?
What happens
If that's the case, what? Then that's not true anymore.
Restart.
Yeah. Actually, you know, all of the arithmetic has already been done with the assumption that there are monopoles.
Yeah, mathematically monopoles exist.
Yeah.
You just have
There's no problem with it at all. But it adds a bunch of terms and would make this course a little bit longer. All right. But this tells us, just as it did with Gauss's law and electric fields, sorry, Gauss's law and the D field in that case. This tells us that B perp in region 1 for a surface has got to be equal to B perp in region 2. The magnetic field is continuous, perpendicular to the surface, right? Parallel to the surface, we use the curl, and we get B parallel to region in region 1 minus B parallel in region 2 is equal to 4 pi over C K, where K is both the bound density, surface current density, and the free surface current density. I can write the same thing with H if I only consider the free. surface current density. And the other condition that can be useful is that A1 is equal to A2. Potential is continuous. All right? So as you're solving problems, you might find that using the boundary conditions can help you through the problem. Turns out that they don't help you as much with magnetic problems as they did with electric field problems. Because with magnetic problems, we really have a vector potential, and we can really only use scalar potential and the Laplacian solutions in regions where we have no current. So inside of a magnetized material, if the magnetization depends upon position, we actually have bulk current and we can't use the boundary condition so simply. All right. Questions? Comments? All right. I'm just going to take a little bit of time now to talk about how matter responds to magnetic fields. And it basically comes down to this. Applying a magnetic field to a material will cause magnetic dipoles within the material to respond. And there are a variety of ways in which they can respond. One of them is extremely complex. Some of them are pretty simple. One is that, let's say I had a gas, and every molecule in the gas has a dipole moment. So I can think in the absence of a magnetic field that I've got a whole bunch of dipoles oriented in whatever directions, random directions, right? And the net magnetic field from all of those dipoles, external magnetic field from all of those dipoles, as long as they're randomly oriented, is 0. And the, let's say the alignment energy that's normally associated with aligning the dipoles of gas molecules is extremely small. It might be 10 to the minus 5 electron volts. And room temperature is like 10 to the minus 2 electron volts. It's actually bigger than that, but it's 2.5 times 10 to the minus 2 electron volts. So room temperature, KT, is really big compared to the energy of aligning those in a typical magnetic, in a strong magnetic field of 1 Tesla, right? So these guys tend to remain overall unaligned. And the magnetic field from this guy drops off pretty rapidly, so it doesn't interact with that guy, the magnetic field from that one. So for most materials, I can think of the magnetic dipoles as being non-acting, interacting with one another. And then I just have to ask, how does each dipole respond to the applied magnetic field? The first way in which dipoles can respond is if I actually have magnetic dipoles in the material, then those dipoles are going to align with, or they're going to have lower energy when they're aligned with the magnetic field. Right? Aligned or anti-aligned? I can't remember which. Ask Professor Lewis. I really respect Professor Lewis. I really do. So, I apply my magnetic field, and the dipoles can align in the magnetic field. And the energy that would be associated with that alignment is going to be of order UB times B, where that's the Bohr magneton, right? For a molecule that actually has a dipole moment already. And the dipoles are going to, on the average, want to align with the magnetic field. So when you have a material in which the dipoles want to align with the magnetic field, but the dipoles are only very weakly interacting, then you call that material a paramagnet. And the strength of that interaction, as I said, this energy is about 10 to the minus 4 electron volts. Much lower than room temperature. So on the average, these atoms remain unaligned in the field. Right? There is a slight average alignment that you get, but it's going to be really weak. Paramagnetism. Under that condition, then it actually turns out that we can write that the H field of the material actually is linearly related to the B field. And we just have a constant relating the two. So this would be a material in which adding B field leads to a slight linear magnetization of the material with the applied field, right? Paramagnetic.
Is it B equals mu H or H equals mu B?
B equals mu H, where mu is greater than 1. And I don't actually remember that off the top of my head, but as I was deciding which way to write it here, I glanced over there and said, oh, H is bigger than B. Oh, sorry, B is bigger than H. So it must be this way.
As long as mu is 1, greater than 1.
Greater than 1. Okay? So that's paramagnetism. Very weakly magnetic. In paramagnetics, if you have a paramagnetic material and you put it in a magnetic field, it will be pulled into the field with a weak force. Right? Then the next thing that we can think about is if I have a choice. If I have a dipole or if I have an electron cloud with no dipole moment, right? And I fix the orientation of this, and I don't care about that. But I fix the orientation here. And then I apply a magnetic field. When I try to change the field inside of this loop, lens comes back to bite us and induces a change in the current around that loop in order to fight the change in the field that we just made. Right? So we're actually causing the magnetic moment to decrease, and then there'll be an interaction with it. But basically, we are inducing, when we turn that field on, we're inducing a magnetic dipole moment in the opposite direction. So there's orientation, right? But then there's also Lenz's law. Turns out that this effect is even smaller. So the energy associated with that is going to be typically something like 10 to the minus 6 electron volts. And so it's a much weaker alignment that would occur. And it turns out then that we can actually only observe these diamagnetic effects when the material that we're working with has no dipole moment of its own. Right? So you have to have the right nuclei, and you've got to have a spin 0 multi-electron state. Right? So spin 0 multi-electron state and no angular momentum. So helium would be a good example. Oxygen turns out to be another. Yeah.
Nitrogen?
No.
Oh.
There's an unmatched electron in nitrogen.
Oh.
It's got an odd number.
In N2?
So it's going to have... Oh, nitrogen gas. Yeah, maybe. I'm sorry, I was thinking of the atom. N2, I'd have to look at the details. But I can tell you for sure that in oxygen and in helium, diamagnetic effects are the strongest effects, right? This energy is in the opposite direction, so I should actually just put a minus there, because the induced dipoles are opposite to the magnetic field that was applied, right? So, and then in that case, it turns out that diamagnetic materials, if you put a little bit of diamagnetic material in a magnetic field gradient, it moves out of the field. It's a weak force that moves it out of the field. And that's actually how we measure the diamagnetic strength of materials. Right? You take a chunk of it, you put it in a strong magnetic field, and you see which way the force on it goes. Literally, you sort of hang a chunk of whatever you're interested in a strong gradient of the magnetic field. Right? So that's called diamagnetism.
And 2 doesn't have any unlined electrons.
So it doesn't have a net spin.
It doesn't have any unpaired electrons.
Well, I mean, that's true.
I could show you.
Right. Yes.
The molecule.
Actually, I'm sure it doesn't have unpaired electrons, but I don't know what the angular momentum of the bonded state is. And it's got to have L equals 0. So I'll allow the chemists among us to work that out. Maybe I'll suggest it to Professor Lewis as a problem.
P-chem isn't on this here.
Okay. Paramagnetic diamagnetism. There's a third case. Yeah.
So it can only be diamagnetic if it's got an even number of electrons.
Yes.
But just because it has an even number of electrons.
That's not sufficient.
Okay, yeah.
Right? It's got to have 0 angular momentum
But not
as well. And the nucleus has got to have no moment.
any other conditions.
Oh, that's about it. All right. Ferromagnetism is much more complicated. All right. In ferromagnetism, neighboring dipoles interact strongly with one another. And you'd actually think that if neighboring dipoles interacted strongly with one another, that if you had a dipole over here which had a magnetic field that went like that, then nearby it's going to do that. I'm going to show you why it's a problem, why you have to think a little bit more deeply about it. And so if there were a strong interaction and I had a neighboring dipole, that neighboring dipole would want to point that way, right? Because it wants to point along with the field that comes from that guy, right? That turns out not to be the case in ferromagnets. Ferromagnets, they do that, right? And the reason that they do that is actually due to chemistry, to bonding. That is, that the atoms find it more energetically favorable for the angular momentum of this atom to be in the same direction as the angular momentum of that atom. And that's because it's energetically favorable to make the bonds with the two atoms in the same angular momentum state, right? And the energy that's associated with that versus that, these are chemical energies now that we're talking about, bonding energies, which typically might be a few electron volts, but then the difference between this and this turns out to be maybe a half an electron volt or a tenth of an electron volt, much bigger than KT. And so neighboring atoms in a ferromagnetic material want to be aligned because quantum mechanics forces them to be aligned, right? In a ferromagnetic material initially, if you just have a material sitting there, there's no preferred direction, and you will end up with sort of randomly oriented chunks of magnetization in the material. One piece will be oriented one way and another piece of the material will be oriented another way. When you apply a magnetic field, though, then those chunks begin to align with one another. The domains begin to align with one another, and you get a net magnetization. And then once the material is magnetized and this guy is aligned with that guy, it likes to be that way, and it's going to stay that way. So a ferromagnetic material is not linear at all in its response. These are linear. You increase the field, the average magnetization increases linearly, and so you can write there. I can write that relationship, okay? But with all interesting magnetic materials, this is not true, right? Unlike in electrostatics, almost all interesting electric materials, dielectric materials, just have a linear dielectric constant. All the ones that we work with in capacitors and all that, they're linear dielectric constant. Not true for interesting magnetic materials. Ferromagnetics have a very nonlinear response. In fact, you have probably seen this. If I apply a magnetic field, and look, I'm not sure which one I'm going to make a drawing and then figure out which one it is. We start with a zero field applied. We apply a field, and the magnetization grows and then saturates. And then as we come back, we find out that it looks like this. Like so. All right. So first time you magnetize a material, initially, actually I'll even put it more. You get strong magnetization with a small applied field. The dipoles align, and they like to be aligned with one another. Then once they're aligned with one another, they don't want to misalign, and you actually have to push it quite a ways in the other direction in order to get them to misalign. So you make a ferromagnet by applying a field and then taking the field back down to zero, for example. Other way. Okay. Yes, that's the direction that I wanted. So that's it. Turn that off.